So, first I want to talk about sampling variability. So when we do this in the classroom, I actually give you all a packet of Skittles, and I have you count the total number of Skittles and the total number of reds that are in there. We then use those in class as an exercise, but since we're on the internet now, can't do that, so we're just going to use other people's data. So the company that owns Skittles says that for the regular red pack, there's 5 flavors in there, and they actually give you 20% of each flavor. Each bag that you get is a sample from the factory. So let's say there's 100 in each bag. Do you think there's exactly 20 of each color in the bag? Well, I personally have always felt like they rip you off. So the reds, like I didn't like the yellows and the greens, actually, and kind of only like the oranges, and until they changed the greens to apple. So I always thought they ripped you off on the reds. In particular, they didn't give you 20%, so we can actually test that. So in a class 25 students, because you can't do it with you guys, they counted the total number of skills in each bag, the total number of each color in each bag, and they calculated the percent of each color. And in particular, the expectation here is that you get 20% unless the Wrigley company is lying, which wouldn't be a shocker, but you know, here's the next slide shows for this class the min number that was in each bag, the max number in each bag, and the mean. So the reason you have to count the total number as well as the total number of each color is you don't get even the same number in each bag. So as you're about to see. So the counts are on the left. The middle thing here is the percentages, and you can see that, you know, the bag percentages, you know, some were 60, some were 77, 50s, like that's why you got to do percents. But if you look at the red percents going down that red column in the middle there, you can see that it does kind of go from what's the low, the min is 10%, it's at the bottom there. The max was 35% of the bag was reds. The average overall is 21%, orange 19%, greens 21%, yellows 20%, purple 18%. It does, even though like there's this wide variability in each bag from 10 to 25% reds, on average it's sort of approaching that 20% of each color in each bag. I hope you see that in the top blue row and the bottom there. So there's a lot of sample to sample variability, but overall there is some overall parameter that is 20% of each color that's in each bag in reality. So the percent red ranged from 10 to 35. Averaged across the 25 bags though, the percent was about 21%, bottom blue. In fact, while there was a large variation, the percent of each color across bags, I mean, one of them is 4%. You see in the yellow, 4% to 40%. When you start combining across multiple samples, that is, you get a bigger and bigger sample, you get closer and closer to the actual percentage that the factory uses, that is the population, 20%. So here's what I hope you get for this. Given we're not doing it in class, you don't get any free candy, it's kind of lamer, but hopefully you see that samples from the exact same population, they really do give you 20% of each color, but they can vary a lot from sample to sample just by chance. But when you get a big sample or you go across multiple small samples, you start to get closer and closer to estimating that true percentage of what's reality in the population, that is 20% of each color. I have no idea if this is going to work when you're not actually getting free candy, so hopefully you still get the lesson. So a little bit more on sampling variability. Again, if you take 2 samples from the same exact population, they're going to differ from each other, almost certainly. They almost always do, right? Same population, you pick a random sample of things or people from that, they're going to vary from the whole population distribution, just the way it works. It's chance. So, for example, I grew up in a household with 4 folks, and we had Lucky Charms. And from bowl to bowl of Lucky Charms, the percentage or sort of representation of the marshmallow things, whatever they are, those freeze-dried marshmallow chunk things, could vary a lot, right? So you're sitting down one morning, you get a ton of marshmallows and only a little bit of that nasty brown stuff, and sometimes you get just a couple marshmallows and not so much of the nasty brown stuff. And so it's yeah, actually my brother seriously did this. He picked out all the marshmallows one time and I got an entire bowl of nasty brown whatever the healthy thing in this is supposed to be. So the variation that you get across samples, even though there is that population, like there's some percentage of marshmallows they put in your Lucky Charms, but even from bowl to bowl from the same box, you get different proportions of marshmallows to brown crud. That's called sampling variability. It's a real thing. So you just saw it with the Skittles. Now you're seeing it with the Lucky Charms as another example in case the Skittles one didn't work. But note that smaller samples have more sampling variability. That is, when you have a smaller sample of a thing, it's even more likely to be different from the population than a big sample. So think of it, if you were estimating like the Skittles exercise, I had you counting normal size Skittles versus those big, huge packs with like 1,000 in them, you're probably going to get pretty darn close to 20% estimate from the big one. You obviously didn't, as you just saw, in most cases with the normal size one, but what about those little Halloween tiny ones, the snack ones? I mean, one extra red Skittle in there is like a 20% change in the total number of Skittles you get, right? So it's small samples vary a lot more. So because samples vary due to sampling variability, we do hypothesis testing. Hypothesis testing helps us differentiate when samples really differ from each other or they're only different due to chance. So you expect things to not be exactly the same, but is that difference you see, is it just like one extra red Skittle or is it like a real difference? That's the whole idea of hypothesis testing. So what is hypothesis testing? Well, it's using inferential statistics, which I realize we haven't actually talked about yet. It's in the sampling lecture, but it's using statistics, tests and things so that you can tentatively decide between two exclusive hypotheses. So you guys have already done this with correlation. There's the null hypothesis and the alternative hypothesis. And the way we do hypothesis testing is similar to how criminal cases are conducted in our courts. We set up two exclusive outcomes, right? Guilty, not guilty. It's actually not innocent. It's not innocent. It's guilty, not guilty, right? And we either reject or retain guilt, right? So we either we retain innocence or we reject innocence is really what we do. So in hypothesis testing, we assume the null hypothesis is true, the HO, until there's just too much evidence that suggests otherwise, and we reject it. That's what we're doing. So you get something really unlikely to happen by chance. You go, yeah, this is probably not chance, it's probably real. So it's kind of like in a court where you assume a person's innocent, and then when you've got a video of them stealing boxes or whatever the heck it was, and then you got their DNA and right, you got motive, you go, yeah, no, this guy probably did it, right? So it's the same thing with hypothesis testing. You assume, nope, nothing going on here, and you only conclude that there is when you get all this evidence suggesting otherwise. So the null hypothesis always says nothing going on here, no relationship, no effect, no difference between groups. You know, sometimes it does have like a direction. You think one group's higher or lower, or the correlation's positive or negative. But even when it has those in there, it always had equal to 0 in the correlation, right? So the idea being the null hypothesis piece that there's no relationship is always a part of the null hypothesis, regardless of what else you think you might find. So again, this corresponds to the assumption in court that the defendant is innocent unless overwhelming evidence is presenting during the trial of guilt, and it leads us beyond a reasonable doubt to reject their innocence. So let's talk about the null hypothesis a little bit more. The null hypothesis, again, always states that the variables being studied are not related, or that the IV has no effect, or that there's no differences between the groups, depending on what kind of study you're doing. So for example, you could say the IV did not affect the DV. That would be a null. The average for the DV is the same for both groups or all groups. That would be a null. The correlation between the variables is zero. You've already used that one. We always assume that the null is true at the start of the study unless we observe enough evidence otherwise that leads us to reject the null. Again, similar to the assumption of innocence in a trial, and if it does not fit, you must acquit. So the alternative hypothesis is that other hypothesis. It always states in some way that the variables are related, right? The IV has an effect, the groups differ, something like that. You can never have an alternative that there's no difference, or that there's zero difference. or zero effect. That's always the null. So the alternative is always that there is some sort of effect, difference, or relationship. So for example, the IB did affect the DB. The average for the DB is not the same for all groups. The correlation between the variables is not zero. The H1 is the one that I always write first, right? We did that with correlation. It's based on the research or the experimental hypothesis for the study. So if we can provide enough evidence from the study that the null is unlikely to be true, we tentatively reject the null hypothesis. That is, we use our sig values for that, right? If we get something that's so unlikely to happen just by chance, it's less than 5 times out of 100, we reject that. It's just a chance finding. We go, no, it's probably real. So again, this is similar to a guilty verdict in a trial. If evidence beyond a reasonable doubt is presented against innocence, we tentatively reject that innocence and we conclude that they are guilty. But like science, where we do multiple studies and change our minds, and you should eat eggs, don't eat eggs, take aspirin, don't take aspirin for heart attacks, right? They do this all the time. Upon further trials, you can overturn results. So the decision to reject or retain is based on what we observe in our data. So we make a tentative decision. That is tentative because, remember, science is dynamic, right? So we never prove anything. We only sort of like have the current state of what we believe to be the case in terms of theories. So we just make a decision about the null. We're not proving anything. So beyond a reasonable doubt in hypothesis testing is less than our alpha level. That is usually 0.05, meaning that there's less than a 5% probability our result is due just to chance. So if the p-value, the significance, is not less than our alpha level, that would be greater than 5% probability the result is just chance, we go, well, there's not enough evidence to reject the null. This could just be a chance finding. You know, just because the person's in the neighborhood of the crime doesn't, or knows the person, doesn't mean they're guilty. That's not enough evidence. That could happen just by chance. It's got to be, you know, you got the tape, you got the DNA, you catch him with the stolen stuff, whatever, there's blood. Then when we get so much evidence, we go, yeah, this guy's probably guilty, right? So note that this is not the same as evidence in favor of the null, okay? Just because we don't reject the null doesn't mean like we prove the null. You never prove the null either, okay? The lack of evidence against the null is not the same as evidence for it, or as I like to say, the absence of evidence is not evidence of absence. Someone make a bumper sticker or write that one down. So, for example, because I know that probably doesn't make sense to you, can you prove there are no unicorns? No, you cannot prove there are no unicorns. You could search the planet, never find a unicorn. You have not found a unicorn. That doesn't prove still there are no unicorns. So your null here would be that unicorns do not exist. Your alternative would be that unicorns do exist. You can never prove that unicorns do not exist. You can't. There's no way you could search and know all animals in all spaces all over the world at all time, right? So, but you can provide evidence against the null. What would that be? Find a unicorn, right? You can actually disprove the null. So if you did find one, you would prove that they do exist, right? And that would make all my nieces very, very happy. So to a coin, and again, I do this normally in a classroom, but if I had a coin and I flip a coin 10 times, how many times would you expect that coin to come up heads? Well, most people say 5. How many heads in 10 flips would be so weird that you would be willing to conclude that my coin is messed up, that it's biased, right? So if I got 5 heads out of 10, would you be willing to say, nah, something's wrong with that coin, it's biased? No, you wouldn't, right? That's kind of what you'd expect to happen. 5 heads, 5 tails. What if I got 7 heads? And right, this is only one trial. It's like a bet. If I flip this 10 times, how many heads would you be willing to say, yeah, something's jacked up with that coin? 7 out of 10? That's getting weirder, right? How about 10 out of 10? If I flipped a coin 10 times, I got 10 heads, would you go, something's messed up with that coin? You probably would, right? That's really, really unlikely. What if I got 0 heads? Well, that's actually equally really, really unlikely. So hopefully you said, yeah, that's also weird, right? That's like a two-tailed hypothesis. I didn't say how it was jacked up or biased. I just said it is, right? So what would the distribution of heads look like if I repeated this 10 flips 1,000 times? What would you expect that to look like? Well, it turns out it's our old friend, the normal distribution. So here's an example of a two-tailed hypothesis with an alpha of 0.01 using coin flips. This is what it looks like. So the actual distribution of heads for 10 coins, or excuse me, a coin cost tossed 10 times, and you do that 1,000 times. This is the proportion of times where you get each number of heads from 0 to 10. And you can see sort of counterintuitively, even though the most likely outcome is 5, it happens 24.6% of the time, it actually doesn't, 20% of the time you get 4, another 20% of the time you get 6. As you get further and further from that middle outcome, you get smaller and smaller percentages of the time that it happens, right? It's more rare. So like when I was saying 10 flips, I get 10 heads. That only happens 0.5% of the time. So out of 100 times, it happens half of a time. So you got to do it 200 times to get it to happen once. It just doesn't happen much, right? So it's very rare. So as it turns out, coin flips are symmetrically distributed. And 1 to 9 heads, that is from 1 to 9, that's about 99% of the time, that's what you would expect if the coin is fair, that out of 10 flips, you get 1 to 9 heads. Boom. So 99% of the time, a fair coin will yield 1 to 9 heads in 10 flips. 0 or 10, those ones that aren't in the little red box there, that would only occur about 1% of the time together. 0.5, you'd get 0. 0.5, you would get 10 out of 10 flips. And so it's really, really rare. Together, that's 1%. So given one run of only 10 flips, because it's kind of like your dissertation. Like you're not going to do your dissertation 1,000 times. You're going to do it once, and you got to make a decision. Is there something going on here that's weird or not? Right? It's exactly what you're doing in your dissertation. So if you got 0 or 10 heads in your if I got 0 or 10 heads in my 10 flips, would you be willing to conclude that my coin is biased? Hopefully you say, yeah, that's really unlikely to occur. Well, that is the equivalent. It turns out 0.5 and 0.5 is 1%, the equivalent of an alpha of 0.01, two-tailed, rejecting the null. So if you're willing to say, yeah, if you get 0 or 10 flips, I am willing to conclude your coin is biased. And I didn't say the direction of bias. You have 0.5 and 0.5 together is 1%. You're using like an alpha of 0.01 to reject the null that the coin is not biased. All right, how about alpha of 0.05? That's usually what we use, right? Not 0.01. So here's that distribution again of coin flips. So note that 2 to 8 heads, if you count all those percentages there, that is about 95% of the time you'd expect from 2 to 8 heads to occur in a 10 coin flip trial. So that would be the expectation 95% of the time. So 0 to 1, that is bottom, just getting 0 or 1, or 9 to 10, that is getting the upper 9 to 10. Well, if you add that 0.5 and 2 at the bottom, 2 and 0.5 at the top, that's about 5%. That would happen about 5% of the times, even when the coin is fair. Like it does happen. You get 0 or 1 or 9 or 10 flips, but it's really rare, right? It only happens together 5% of the time you get one of those outcomes. So that's 2.5, 2.5, that's 5% total. So given one run of 10 flips, and again, tuition is expensive, so like you got to get out of school at some point. You can't do your dissertation forever trying to prove truth, because you can't. Would you be willing to say my coin is biased if I got 0 or 1 or 9 or 10 heads in my 10 flips? If so, guess what? That's the same thing as using an alpha of 0.05 two-tailed to reject a null hypothesis. You're saying if you get something that would only happen 5% of the time just by chance, I'm going to conclude your coin is biased. There's some sort of other thing going on here. So hopefully this works as a metaphor here. All right, so how about 0.05 one-tail? What would that look like? So first of all, my hypothesis would have to be different, right? I'd have to say this coin is biased in favor of heads. There's our distribution, or tails, right? But let's do heads. So less than 7 heads occurs about 95% of the time in 10 flips for a coin that is not biased in favor of heads. All right, you would get 0 to 7 heads. Even though this is the 0 and 1 at the bottom end is rare, that wasn't my hypothesis. I'm saying it's biased in favor of heads. So we put all that probability on the upper end of this distribution for rejecting the null. So 7 or fewer, that happens about 95% of the time if the coin is not biased for heads. So 8 or more heads occurs about 5% of the time in 10 flips. So if the coin is not biased, that is, even if the null hypothesis is true, there's, the coin's fair, sometimes you still get 8 or more heads in a flip of 10, right? It's just really unlikely. In fact, it only happens about 5% of the time. So that 5% is all in one tail of the distribution. You guys see where the name comes from now? So if given 10 flips, I get 8 or more heads, would you be willing to conclude that the coin is biased in favor of heads? If you said yes, that's the equivalent of using an alpha of 0.05 one-tailed to reject the null hypothesis. This kind of makes sense to me, but I teach this for a living, so I hope this kind of helps you understand this whole hypothesis testing thing. So it's just, we reject the null when we get something that's really unlikely to happen by chance if the null hypothesis is true. And the null here is the coin is actually not biased. It's okay in favor of heads. All right, so how do we write null and alternative hypotheses? See, we're moving into means now instead of correlation, so we write things a little differently. Instead of how R is related to 0, which is how we wrote these hypotheses for correlation, we're going to be comparing samples to each other, that is means to each other, their average scores on things, or sample to a population. We're going to do all sorts of crazy stuff, counts to counts. So a two-tailed hypothesis that the coin is biased, you would is in words, what number of heads is so unlikely for a fair coin that we would reject that it's fair using alpha of 0.05. So the research hypothesis is that the coin is biased, right? That's the researcher's hypothesis. It's not specifically biased for or against heads, so both too few or too many heads supports the hypothesis, right? If just saying the coin is biased, well, it could be biased for heads or against heads, right? Which I guess is 4 tails. But we're just saying, look, the coin's biased. So that is our research hypothesis. How would we write that? Well, you'd say the number of heads will not be chance. That is, the number of heads is going to be either 1 or fewer or 9 or more, right? So that corresponds to that lower 2.5 and that upper 2.5% total is 5% of the time. You would expect that to happen just by chance. If we land in one of those two regions, we are going to say, yeah, this coin is biased. Gets too few heads or too many heads. So that is the 5% that is consistent with a two-tailed alternative hypothesis. So the null then is everything between 2 and 8, right? If I get between 2 and 8 flips, or heads in my 10 flips, you'd say, yeah, that coin is totally consistent with the null. Okay, what we got is not that weird. We're only rejecting if we get something a very few number of heads, 0 or 1, or way too many numbers of heads. And again, this is two-tailed because we didn't say the direction of the bias. We just said the coin's biased, right? It could be for or against. So what if I said instead the coin favors heads? So I'm picking a side here. I'm picking a tail. That's why it's called one-tailed. It favors heads. What number of heads is so unlikely for a coin that doesn't actually favor heads, so unbiased coin, that we would reject that it doesn't favor heads using alpha of 0.05. So the research hypothesis, again, but in this case, is that it favors heads. So only too many heads supports this hypothesis, right? So if we get too few heads, that doesn't support that it's biased in favor of heads, right? It's biased against heads. So when you pick a side, you're hedging your bet here, right? You're saying it's this way and only this way. And we ran into that with correlation where it was significant. It was like a real relationship, but it wasn't the one we thought it was going to be. And so we were wrong. We couldn't fully reject the null. Same thing. So our alternative here is that the number of heads will favor heads. That is, we're going to get so many heads in our flip that it's really unlikely to happen by chance. And we're using alpha of 0.05. So it's this upper percent. If we get 8 or more heads, we're going to say, yeah, this coin is biased. Those results all support our alternative hypothesis. So what is consistent with the null? Well, 7 or fewer, right? You get anywhere in that region, it's all in support of the null. That is, the coin is either not biased or it's not biased in favor of heads. So the decision to reject or retain, like one of them's right and one of them's wrong, but you don't actually know that in your study. You never know that. Okay, that's what replication's about. So you don't get to do your dissertation 1,000 times. You only get one shot, like M&M, to make your decision. So if I flip a coin 10 times and it yields 10 heads, does that prove the coin is biased? Well, no, we would conclude that in the study, right? We'd say, okay, well, evidence suggests the coin is biased. That's what we conclude, but we didn't prove it, okay? There could be other explanations. Could be wind currents. So what if you repeated those 10 flips and you didn't get 10 heads? Did you prove it wasn't biased? Well, no. So the whole point here is a study doesn't prove anything. We just tentatively decide things. We have to replicate things or repeat studies in order to know what truth is in science. And that goes back to week 1, lecture 1, right? So our decision to reject or retain the null is based on inferential statistics you learn in this course. And they tell you the likelihood of obtaining our findings by chance if the null is actually true. That is a wrap. So let's go back to our court metaphor on hypothesis testing. So rejecting or retaining the null, it's similar to decisions in a criminal trial. The more evidence you present against innocence, the more likely it's going to be rejected, right? So also like a trial, we never know really whether the null or the alternative is true. You don't actually know if the person killed him or not. I guess if you have a tape or whatever, but you know. We weigh the evidence generally and we make decisions based on the probability of events occurring by chance or not. So you were there, your DNA is there, you have their property, you know. So as you get more and more evidence against the null, you reject it. So if we reject the null, we conclude the variables are related. That is, there's too much evidence against concluding the variables are not related. I know it's like a backwards logic. So this is what we mean when we say statistically significant. We're saying these variables are related. If we retain the null, evidence is insufficient to conclude that the variables are related. We didn't prove the null again. That's why it's worded so awkwardly. This is referred to being, this means not statistically significant. So if there's not enough evidence to reject the null, that is, we retain the null, we say it's not statistically significant. So there are correct decisions we make when we choose to reject or retain a null. So let's talk about those first. Let's be positive. There are 4 possible outcomes of hypothesis testing decisions. So what we have here on the left side is the decision, whether in your little study you decided to retain the null or reject the null. Now, the top here is the true status of the null, which you don't know. Okay, this is a didactic exercise. So let's pretend you're omniscient and somehow after you did your study, you knew whether you made the right decision or not. That is, whether the null was true or not. There are 2 correct decisions and there are 2 incorrect decisions that you can make. The 2 correct decisions are, number 1, retaining a null when it is true. That is kind of like saying someone is innocent. You retain that if they're not guilty. So this box up here where you've retained, and then on the column, the null is true, you've retained something that's true. You have said there's no difference between the groups, there's no effect, and in reality there wasn't. The other correct decision is rejecting something that's false. That is like rejecting innocence when the defendant's actually guilty. So again, that box is when you've rejected a null that's false. So you've said there is a relationship, because remember the null always says there is not a relationship. There is a relationship, there is a difference between the groups, whatever it is, and in reality, there was. You've made a correct decision. So remember, retaining something true is good, and rejecting something false is good. And it turns out that alpha, our alpha level in our study, is actually our likelihood of, or 1 minus alpha is our likelihood, sorry, of landing in the upper left box, and our power is our likelihood of landing in that lower right box. So there's also 2 bad decisions on here, right? So the 2 incorrect decisions are, number 1, what we call a type 1 error. That is when you reject a null when the null was true. So again, back it up a sec. What's the null say? The null says there's no difference between the groups, the variables aren't related. You've rejected that when really the groups aren't different. Okay, the variables aren't related, but you've said they are. That's what we call a type 1 error. And that is our alpha level. So that alpha in a study, usually 0.05, means we have a 5% chance of making a type 1 error, that is rejecting a null when we shouldn't have because it was true. So that is our alpha level, rejecting a true null. And you know it in your study usually. So that is considered the worst type of error. That's like sending an innocent person to prison, right? You said, no, there is a difference here, or no, there is an effect, or in my world, no, this drug is better for treating this disease, when really it wasn't. Okay, that's bad. The other type of error is what we call a type 2 error, and it's when you retain a null when it's false. Okay, so again, the null says no difference. You retain that, but in reality there was a difference, okay, or there was an effect of one variable on the other. That's the type 2 error. So that's this upper right hand box. You've retained something that is false, and the sort of Greek letter for that is beta, and that is your probability of making a type 2 error. That is, you did not reject a false null. Okay, that's your probability of not rejecting a false null. And we actually don't know that usually in studies. Instead, we focus on power, the one below it. Okay, so 1 minus beta is power, your ability to reject a null when you should, which we've got a lecture or two coming up on. So again, important stuff on here. There's 2 correct and 2 wrong decisions in hypothesis testing. The 2 wrong ones have special names. One's called type 1 error. That's when you reject a null that you should not have because it was true. A type 2 error is when you've retained a null that is false. So that is beta. The former is your alpha. So it turns out type 2 error is when you don't convict a guilty person, right? So they were guilty, but there just wasn't enough evidence. That is a type 2 error, okay? But again, it's considered less of an error, right? Sending an innocent person to jail is considered worse. So high alpha, or excuse me, low alpha, high power. The goal in your study is to reach the correct conclusion based on the data, okay? So the goal is not to reject the null. The goal is to reach the right conclusion. We're trying to be scientists here, right? Not just write exciting papers. So how do you reach the right conclusion? Well, you have low alpha, and we typically use alpha of 0.05. Occasionally we use 0.01. We will occasionally in this class as well. That means there's a 5% chance of making a type 1 error. And we want low beta, which again we never talk about. We really say high statistical power, which is 1 minus beta. So statistical power is your probability of rejecting the null when it's false. That is finding an effect when one truly does exist. So statistical power is your probability or ability to reject a null when you should, or find an effect when one truly does exist. That is your ability to say, yeah, these two things are related, or this drug really is better. So that's your power. So it's a likelihood you'll be able to detect an effect or a relationship when one truly does exist. So there's a goal for this. Not only do we try to keep alpha no more than 0.05, we try to have statistical power of 0.8 or higher. So again, everyone hates decimals, so scooch the decimal over. We want 80% power, right? At least in our dissertation. And we will talk about how you do that. So just because something's statistically significant doesn't mean you care. Or you should care, okay? Statistical significance, yeah, there's a relationship. That's what that means, okay? The variables are related, the groups differ, whatever. But it could be the case that, yeah, they differ, but not by much, so why do I care, okay? So if you reject the null, it doesn't necessarily mean you should care. You can reject the null, but the variables aren't very strongly related. They're related, but yawn, not a big deal. So here's an example. So let's say you got 2 groups, one that takes a really expensive GRE prep course and one that does not take a GRE prep course. And the group sizes are large enough, right? So you can reject the null even if the expensive course group only does 10 points better out of 1,000 possible points on average, okay? So yeah, they took this course and they did better, but it's like 10 points out of 1,000. It's not much, okay? So yeah, the course improved their scores, but so not by any sort of meaningful amount. This is where it's statistically significant, but not meaningfully significant. So, I mean, this is sort of a cost-benefit thing, right? So this small difference in points is not very meaningful because the cost is high for the course. So statistical significance does say, yeah, there's a difference, but doesn't necessarily mean you care. So that's why we have these measures of effect size. So measures of effect size are calculated for most of the inferential statistics that we do, and they tell you how meaningful the relationship is between the variables, how large of an effect the IV had on the DV, what percentage of variability you can predict in one variable from the other. Those are your measures of effect size. So R squared in correlation, for example, was a measure of effect size. So it told us how meaningful the relationship was between the variables, what proportion you could predict from one variable in the other. So hopefully this helps.